For this video, you may want to print out the Student Task Statement document, or PDF, and follow along while watching the video. We learned in a previous lesson that repeated multiplication can be represented by using an exponent. In the warm-up, one way you could have solved the problem was by simply calculating the numerator and denominator and dividing them. In the numerator, 2 to the 5th power is equal to 32, 3 to the 4th power is 81, and 3 to the 2nd power is 9. So 32 times 81 times 9 is 23,328. In the denominator, 3 to the 6th power is 729, and 2 to the 4th power is 16. So 2 times 729 times 16 is also equal to 23,328. Because the numerator and denominator are equal, when we divide them, the result is a surprising 1. It is important to note from the warm-up that any number divided by itself is 1. This will help us understand our next activity called dividing powers of 10. The table given has 3 columns. The first column is an expression in which 2 powers of 10 are being divided. The middle column shows the same expression in expanded form, and in the last column, the expression is written as a single power of 10. You are asked to complete the table to explore patterns when dividing powers of 10. You may skip a single box, but must be prepared to explain why you skipped it. In the first row, the expression given is 10 to the 4th power divided by 10 squared, or 10 to the 2nd power. When expanded out, it is written as 4 factors that are 10 in the numerator and 2 factors that are 10 in the denominator. Notice that there are 2 sets of factors that are 10 that exist in both the numerator and the denominator, but there are 2 extra factors that are 10 in the numerator. This can be rewritten like this. I remember from the warm-up that any number divided by itself is 1. So 10 times 10 divided by 10 times 10 is equal to 1. There are now 2 factors that are 10 remaining, which can be written as 10 squared, or 10 to the 2nd power. In the next example, we are given the expanded form. In the numerator, there are 5 factors that are 10, and in the denominator, there are 2 factors that are 10. Because this is repeated multiplication, it can be expressed as 10 to the 5th power divided by 10 squared. Notice again that we have 2 sets of factors that are 10 in both the numerator and the denominator. But this time, there are 3 extra factors that are 10 in the numerator. This can be expressed like this. Again, 10 times 10 divided by 10 times 10 is equal to 1. And the 3 remaining factors that are 10 can be written as 10 cubed, or 10 to the 3rd power. In the third example, we are given the expression 10 to the 6th power divided by 10 to the 3rd power. We can write it in expanded form by showing the repeated multiplication. This time, I notice that there are 3 factors that are 10 that the numerator and denominator have in common. And there are 3 extra factors that are 10 in the numerator. This can be expressed like this. Again, 10 times 10 times 10 divided by itself is equal to 1. And the 3 remaining factors that are 10 can be written as 10 cubed, or 10 to the 3rd power. In our last example, I notice that the exponents are much bigger this time. In order to write my expression in expanded form, I would have to multiply 43 factors that are 10 in the numerator and 17 factors that are 10 in the denominator. I don't think that'll fit in that little box, so this is going to be the box that I skip. However, if I look at the pattern of the other examples, I can figure out how to write the expression as a single power of 10. In the first example, the difference of the 2 exponents, 4 and 2, is 2, which is the exponent of the single power of 10. In the second example, the difference of the 2 exponents, 5 and 2, is 3, which is the exponent of the single power of 10. And in the third example, The difference of the two exponents, 6 and 3, is 3, which again is the exponent of the single power of 10. So if I follow this pattern and I subtract the exponents 43 and 17 in the expression, this will give me the exponent for the single power of 10.